One of our biggest challenges this semester will be dealing with very large numbers. Things that you just add adjectives in front of it, like, oh, it's really, really large, or it's so huge. And I probably in the first video said tremendously and ridiculously. Um, but that only gets you so far, right? That gets you to an understanding of um, sort of a first level of how big something is. But we're going to be dealing with things that are bigger and bigger and bigger as we move from the Earth out into the solar system, out into the galaxy. So we want to do better than this. And so in this video, what we're going to talk about are some helpful ways to put large numbers into perspective. So let's take the example of the Earth and the Moon, since that's the first thing that we'll come to when we leave the Earth. It's really far away. The picture here on the screen shows you to scale how big the Earth and Moon are and how far away they are, right? Now, you can see visually how far away they are, but how can we talk about it? How can we talk about this distance? I'll give you the number in a second in kilometers, but the key is to make a helpful comparison. That will help us put these numbers into perspective. The distance is 384,000 kilometers, a really big number. Okay, what can you do with that information? What can your mind do with that information? How can you understand the number? So we want to compare it to something that we can understand, and the biggest thing that we're familiar with is the Earth itself. So let's compare it to that. Now, when I say compare it to, what I really mean is look at the ratio between. And that will be true throughout the semester. So if I say, let's compare to this, compare a number to this, what I mean is look at the ratio between them. Find out how many times one can fit into the other. That's the way we can make a useful comparison. So I take the Earth's diameter, which is 12,742 kilometers, and I can divide it into 384,000 kilometers, which we see here. And what you find is that gives you 30.1. That means that there are about 30 Earth diameters in between the Earth and the Moon. Now that's a number that I can wrap my mind around. I can think about how big the Earth is. If you've traveled, across the country or out of the country, you've got some sense for how big the Earth is. Well, the Moon is 30 of those Earths away from us. That's a much better way to think about the distance than 384,000 kilometers. So in general, what we want to do is take a really, really big number, like 384,000, and put it into a number that's, let's say, like less than 100. You can count to 100 in a reasonable amount of time, so we can think about numbers that are within 100 relatively easily. Another tool that will be incredibly useful for us is scientific notation. I imagine there are some of you that are expert at this. You know exactly what I'm talking about, and others might need a refresher. If you do need a refresher on scientific notation, there are some Khan Academy videos here. Briefly, I think the best way to think about scientific notation is just literally what it is telling you to do. So I have taken the number 384,000 and written it in scientific notation. And so reading this number, what it means is you take 3.84 and multiply by 10 to the fifth power. Now what that effectively does is it would move the decimal place 5 places. Okay, so thinking about it backwards, if you start out with a number like this, you just count the places. So the decimal point would be here. You count the places that you would have to move the decimal to get to the first digit, and in this case it's 5, and then you just write times 10 to the fifth. Okay, so when you get a large number, you would have to count the places to consider that number. Scientific notation does that for you already. One more point about scientific notation before moving on. Since we'll use it a lot and we'll talk about things that are in different scales, it's helpful to remember that 10 to the third power, so a 1 followed by 3 zeros, is 1,000. 10 to the 6 would be a million, and 10 to the 9 would be a billion. So when we see 10 to the fifth, if we know 10 to the 6 is a million, we know that this is less than a million, right? And it's sort of just helpful to keep these specific cases in mind going forward. All right, let's take another example. And let's leave the solar system and go to our nearest neighbor star, which is Proxima Centauri. It is this many kilometers away. Okay, so let's think about what this is. So this would be 1,000, million, billion, trillion. So it's 39,740 billion kilometers away. Again, it took me a second to think through all that. So a faster way to gauge the number is in scientific notation. In scientific notation, there are 13 places coming after the 3, so it's 3.974 times 10 to the 13 kilometers. But still, putting it in scientific notation is a good step, but it doesn't put the number into perspective for me necessarily. The trick we used last time with Earth diameters, that's not going to work. I mean, you could try it, but you probably can guess it's not going to work for a number that large. So what can we do? Another trick that we often use, and we do this all the time, is the time that it would take to get there. Now we think about it in terms of travel time by car, maybe even plane. Boston's about an hour away from Manchester. New York is like 5 hours away from Manchester. So we think about distances in terms of times to get there pretty regularly. In fact, I think if you Google search how far to X city, Google will probably tell you the time it would take to drive there. But we're not driving to a star. In stellar distances to stars, what we use is the travel time of light. Light is incredibly fast, 3 times 10 to the 5th kilometers per second. So a little less than a million kilometers per second. Let's use that number to figure out how far to Proxima Centauri. So we're going to need to do a little bit of math here to put it into perspective. And it starts by thinking about speed is distance over time. We want the time. So if speed is distance over time, then time is distance over speed. So we take the distance, divide by the speed, and this is the result, 1.3 times 10 to the 8 seconds. So still we have a big number, right? We're still at a very big number, but we're on the right path. We've got this many seconds for light to get there. So let's jump from seconds to years, and we can convert this. I usually use Google to convert things. You can do this by hand. You could figure out how many seconds there are in a year, right? Because you know how many seconds in a minute, minutes in an hour, hours in a day, days in a year. So you could get there, but it's faster to just Google it. So Google convert 1.3 times 10 to the 8 seconds to year, and you'll find that it is about 4 years. 4 is a number we can work with. So Proxima Centauri is about 4 light years away. That means that the light from Proxima Centauri takes 4 years to get to us. Okay. Now, it's not a perfect answer, right? Because do you really understand what a light year is? Yes and no. I mean, in theory, hopefully it makes sense what a light year is. But where it will be really valuable is comparing the distances to other stars. We just can't use any human lengths of measurement to gauge distances when we're talking about stars. We can't compare it to the size of the Earth. That just leaves us with too many large numbers. But once you have some sense of a light year, right? That's the distance that light will travel in a year. Then you can start to build an understanding of distances to stars all across the galaxy and then between galaxies themselves. And so if we ever wanted to take a trip to Proxima Centauri and we invented a spaceship that could travel at the speed of light, it would still take us about 4 years to get there.